Hello and welcome to a Group 19 feature film on an essential component to the modern world and everyday life. Without this system, even the basic tasks in life would be infinitely more arduous.
Hey baby, do you want to see my powertrain?
Ooh baby, it would drive me wild.
Yeah? Well, let's get this up.
We'll start from the top. This is the engine. Fuel goes in with air, magic happens, and nasty stuff comes out the end. But more importantly, things spin.
The power from the engine is then passed to the powertrain. We will now take a closer look at these components.
The flywheel is the first link in the chain. Original flywheels consisted of just a single metal disc. In order to be balanced, these needed to be drilled. They were later developed to dual mass flywheels. These significantly reduce vibration because they can be tuned specifically to the engine, taking into account both torque and load curves. These components make up the dual mass flywheel. The dual mass flywheel, as the name suggests, contains two separate flywheels. The inner flywheel sits like this and is surrounded by two springs. This is to help counter the rhythmic motion of the crankshaft by allowing the inner flywheel to move slightly in the opposite direction to the outer flywheel, causing an out-of-phase motion, reducing the overall amplitude of the vibrations. This is the outer flywheel. It adds extra mass and has teeth around the edge, which are used to connect the starter motor to the engine. The final mass sits inside, and the clutch plate sits on top, here. This high-friction clutch plate spins with the flywheel, and the pressure plate, here, applies pressure whilst the clutch is engaged, transferring power from the crankshaft to the gearbox.
After the flywheel and clutch comes the gearbox.
This chunky hunk of metal is the gearbox. Without this, your car would have extremely poor acceleration from rest and a much lower top speed. Also, without the gearbox, you'd have to be travelling at approximately 15 miles an hour before you could fully engage the clutch. The addition of the gearbox allows for different power outputs for different tractive forces and conditions. Also, it allows for a neutral and a reverse gear. The clutch is connected to the input shaft, which houses free rotating gears. When you select a gear using the gear lever, you move these dog collars into position so they connect with the desired gear. This fixes the free rotating constant mesh gears to the output shaft, which completes the drive connection. Synchro mesh allows for smoother, quieter gear transition by employing a clutch type mechanism. This is a brass cone that connects with the gear to bring it to the correct speed before fully engaging. This is reverse. Notice how it has an extra gear to give opposite rotation of the output, leading to, of course, a backwards motion. Before constant and synchro mesh gearboxes, gears would slide together axially. Gears would crash together, making a lot of noise and taking a lot of effort from the driver. More modern gearboxes employ helical gears. These give a much smaller contact line, which localizes the error in gear connection. This gives a better, smoother and quieter gear connection.
After the gearbox, power is transferred via the propeller shaft, or prop shaft.
This is a fully assembled powertrain from a Ford Transit van. Underneath the blue casing we've got the flywheel, the clutch, and this is the gearbox. It's all connected to the rear axle via the prop shaft. This prop shaft is sectioned, and each section is connected via universal joints. The section setup reduces vibration in the system by minimizing sag. This is a sectioned prop shaft. As you can clearly see, it's hollow, which makes it lighter and further reduces the probability of sag. Unfortunately, a side effect of this is a bell-like effect when a torque wave passes through the system. We can minimize this effect by putting in a damper, like this cardboard tube. By doing so, we get a noise of the same magnitude, but a different and less undesirable order. This is a universal joint. It's integral to the whole system as it allows for the height change between the gearbox and the differential, and it allows for movement in the suspension. Also, this setup allows for uniform power output. Without the universal joint, you would have sinusoidal angular velocity. Finally, the whole system is connected to the carriage by rubber mounts, which reduces vibrations.
The prop shaft transfers power to the differential. When a car is travelling in a straight line, both wheels travel at the same rate. However, when a car navigates a corner, the outside wheel wants to speed up, as it has a greater distance to cover, which can cause the wheel to slip. If we now put a differential between the wheels, they can spin at different rates whilst both being powered.
Using our generic modelling kit, we have here a demonstration of a differential. The differential is an essential part to the automobile as it allows you to power both rear wheels and turn at the same time. This model has 3 spinning wheels. If we want to power both wheels at the same time, we could put this bar here. This locks the motion. However, this does not allow for turning as the wheels are forced to spin at the same rate. Adding a rotating bar instead allows the wheels to spin briefly at a different rate. This is fine until you turn too far and the bar no longer connects. To combat this, we add another cog here. This allows for constant turning. To increase strength, we add another cog here. As you can see, if there is no resistance to either wheel, they both spin at the same rate, but to turn, they can still do so. This is the working principle of the differential. And here's one we butchered earlier. This housing contains the setup we modelled earlier. Here you can see the power is supplied to the ring gear via the input pinion, which is connected to the prop shaft. When these spiral bevels were introduced to reduce noise, a new extreme pressure lubricant was developed so that the oil film would not rupture under the more secure contact. In most modern rear-wheel drive cars, a lowered pinion is used. This not only allows for more space in the cabin, but also allows for a stronger, larger pinion gear.
Finally, power is transferred to the wheels.
The wheel is the last piece in the puzzle. It acts as the final form of gearing between the engine and the road. The bigger the wheel, the harder the engine has to work because of the moments involved. Also, the pneumatic tyre acts as secondary suspension, cushioning out the road as you drive.
To summarise the effect of the powertrain, a 99 Subaru Impreza running at 3000 rpm will have a post-gearbox drive of about 4065 rpm. The differential then steps this down to a wheel rotation of 914 rpm. So that was the rear-wheel drive powertrain. But on today's roads, we increasingly see front-wheel drive vehicles. The successful application of front-wheel drive came around 1930, and the setup has gained popularity ever since.
But why does today's market favour the front-wheel drive setup when rear-wheel drive has clear advantages such as better balance in the car? They have a simpler system giving better serviceability, and rear-wheel drives don't suffer from torque steer. This is mainly an economic change pushed by the industry with 3 main factors: efficiency, safety and cost. The modern market demands cheap, safe cars. Rear-wheel drives are more expensive to manufacture than front-wheel drives, immediately making them less desirable in today's market. Furthermore, they take longer to assemble, as in front-wheel drives, the engine and powertrain can be pre-assembled, then pretty much dropped into place. This works in the manufacturer's favour as they can spend less on labour and retail lower priced cars with higher profit margins. Also, without a prop shaft running to the back of the car, there is more space in the cabin for passengers and luggage. Moreover, front-wheel drives are lighter, making them more fuel efficient. Finally, with the weight over the front wheels, better traction can be maintained on slippy surfaces like snow and ice. However, modern traction control in rear-wheel drives can be as effective. This all points in favour of the cheaper front-wheel drive system, and hence the shift over the years to the front-wheel drive dominated market we have today.
Wow, I have to consider being driven from the rear in future.
Whew. And on that bombshell, it's time to end. Good night.